So let's say we have the next example that says minimize z equals to 2x1 plus 3x2, and the constraints are x1 plus x2 greater than or equal to 9, x1 plus 3x2 greater than or equal to 15. The last constraint is 2x1 minus 3x2 is at most 9. Both the variables are non-negative. So let's solve this using the graphical approach. Let's say we color these constraints. Let's say this is the blue constraint, this is the red constraint, the green constraint, and the yellow constraint. So we'll just plot this. So why only the first quadrant? Because of the yellow constraint. The yellow constraint says x1, x2 both are non-negative. So that is why only this region. So the arrow is right of the x2 axis above the x1 axis. Now we plot the first constraint. So plot it as a line first. So let x2 be equal to 0. So x1 is 9. So the value for x1 is 9. So let's say is 9 comma 0. If we put x1 as 0, so x2 is 9. So x2 is 9 gives you, say, this. This is 0 comma 9. We plot the line. That is this line. And where is the region? Say I just shade this as blue. Now where is the region? How to check? Put 0 comma 0, 0 plus 0. So 0 plus 0, if you see in this, you get 0 plus 0 is greater than 9, greater than or equal to 9. But this inequality is not satisfied because 0 is not greater than or equal to 9. So that means in this constraint says that you be away from the origin. So this is in fact the region. So blue says to be this side. Okay. Now we plot the red constraint. So for the red, put x2 as 0. So x1 is 15. So let's say this is 15 comma 0. Put x1 as 0. So x2 is 5. So x2 is 5. 0 comma 5. And we plot the red constraint. The red constraint passes through this. Where to stay? The red, if you put the point 0 comma 0, so 0 plus 3 into 0 is 0. So 0 plus 0 is greater than or equal to 15. Again, this is a violation. So for violation, you go away from the origin. So that means the red says ki idhar raho, away from the origin. Now we plot the green constraint. So the green x1 is equal to 9 by 2, that is 4.5. So 4.5 is say this, say 9 by 2 only, right? 9 by 2 comma 0. और इसके लिए you set x1 as 0, so x2 becomes minus 3. So if x2 is minus 3, so it's there somewhere. So pass the line. This is the green constraint. Now if you put 0 comma 0, so 0 minus 0, this is satisfying. 0 minus 0 is less than or equal to 9, which is true. So we have to be towards the origin. So towards means if you extend this, you extend this. So towards means this side. So this is this, this, this. So where is the common point? The common point is in fact, if you see, the common point is, so where is the common region? The common region here is in fact this region that is open-ended. What is the region? See, can this be the region? First, first we'll negate what cannot be the region. Can this be the region? This cannot be the region because the red is violated. Red says to move ahead. Can this be the region? This cannot be the region because in this the blue constraint is saying कि यहाँ पर it will not get satisfied, so this cannot be the region. So this is not the region. This is not the region. Can this be the region? Because the green is not satisfied, this cannot be the region. Can this be the region? Green cannot satisfy this. Can this be the region? Red is not satisfying. Can this be the region? This also cannot be the region because green is again not satisfying. So what is left is in fact this region. See, in this region, open-ended region, every inequality is getting satisfied. ये blue के लिए भी सही है. If you put this point, ये blue के लिए भी सही है, green के लिए भी सही है, red के लिए भी सही है, और non-negativity के लिए तो सही है. So what is in fact the common region? The common region is this boundary, this boundary, this boundary, this boundary, and this boundary. So in fact, this is an open-ended region because you do not have a closed region. So everything in this open-ended region is the feasible region. So this is the region. Now how to get the answer for our problem? So first of all, see the corners that are clearly visible to us. The corners that are visible are this corner, this corner, this corner. But this region is not closed and bounded. That means you cannot directly find only these corners and evaluate your objective. What you need to do in these cases is, let's see, just extend this because it is a straight line, same line. What you need to do in these types of cases where the region is open-ended. So this is for cases that are open-ended, that are having open-ended regions. That means the region is not something like this कि वो हर तरफ से बंद हो. यहाँ पे ये रीजन कौन सी तरफ से बंद नहीं है, ये ऊपर यहाँ से बंद नहीं कर पा रहे हो आप. सो व्हाट यू हैव टू डू, impose an hypothetical constraint. Let's say the constraint that you enforce is a hypothetical one, and let's say that constraint is, आप इस रीजन को एक ऐसी कंस्ट्रेंट डालो जो डालते ही आपका रीजन बंद हो जाए. सो लेट्स से मैंने एक कंस्ट्रेंट ऐसी मार दी यहां पे. सो नाउ इज द रीजन क्लोज्ड. अब तो ये रीजन क्लोज ही हो गया. तो करना क्या होता है, मैंने एक कंस्ट्रेंट करी x2 लेस देन इक्वल टू सम कैपिटल M, और ये डालते ही क्या हुआ, मैंने एक कंस्ट्रेंट बनाई x2 इक्वल टू M लाइन बनाई, और मेरे को चेक करना है कौन सा रीजन है. तो मैंने 0,0 डाला, तो 0 is definitely less than capital M because M is this value is positive, and in this case let's say M is very large. मैंने एक बहुत बड़े हाइट पे एक कंस्ट्रेंट पैरेलल मार दी जिससे ये रीजन बंद हो गया. So the region is in fact towards the origin because 0 is x2 and 0 is less than M, where M is tending towards infinity. M is very large. यानी कि ये हाइट जो है, ये जो हाइट है ये बहुत ज्यादा है. So now if you see I get more corners, and what are those corners? These are these hypothetical corners. एक तो ये आया और एक ये आया. Okay, so what is that corner? इस कॉर्नर का क्या कोऑर्डिनेट है? इट इज 0,M. और इसका क्या कोऑर्डिनेट है? इट इज लाइंग एट द इंटरसेक्शन ऑफ द ग्रीन कंस्ट्रेंट एंड योर हाइपोथेटिकल कंस्ट्रेंट. तो हाइपोथेटिकल कंस्ट्रेंट में आपको y का वैल्यू तो पता ही है, x2 का वैल्यू इज ऑलरेडी नोन टू बी M. इस M को पुट कर देना ग्रीन में तो आपको वैल्यू आ जाएगा x1 का. तो इस ग्रीन में पुट करके देखते हैं. सो ट्वाइस ऑफ x1 minus thrice of m is equal to 9. So x1 is nothing but 9 plus 3m by 2. So the value for x1 is, it is 9 plus 3m by 2. This is x1 coordinate and x2 is m. So these are the two new coordinates that you get, this one and this one. और पहले से तो ये थे ही. So now we list all the corners. You can't just evaluate the corners, this corner, this is not the corner. You can't just evaluate on this and this and report whatever is the minimum, because minimum पूछा है. तो बस इन 3 corners पे निकाल के काम नहीं चलेगा. आपको अपने रीजन को पहले बंद करना पड़ता है, because the region, to apply the fundamental theorem of linear programming, the region has to be closed bounded. और अगर ये लाइन नहीं होती यहाँ पे, अगर ये लाइन नहीं होती तो रीजन क्लोज नहीं है और बाउंडेड नहीं है. सो दैट इज वाई वो कंस्ट्रेंट डालिए जिससे रीजन हमारा क्लोज एंड बाउंडेड हो जाए. सो नाउ यू कैन लिस्ट द कॉर्नर्स. सो हाउ मेनी कॉर्नर्स डू वी हैड? से दिस इज द कॉर्नर, से ए, से दिस इज बी, से दिस इज सी, this is D, and this corner is say E. So we have corners A, B, C, D, and E. The simplest corner is in fact B. B का coordinate is 0, 9. C का corner is 0, capital M. D का corner is 9 plus 3M by 2, M. तो कौन से corners निकालने हैं? A and E. So A is at the intersection of the red constraint and the blue constraint. So this is the red and the blue constraint. So if you subtract, so this goes and this becomes minus 2x2 minus 6. So x2 becomes 3. So x2 is in fact 3. x2 is 3 and x1 is 6. So this is the corner A. Now to get to corner E, E lies at the intersection of, this is E, it lies at the intersection of the green constraint and the red constraint. So green and red, these are the constraints. So what you simply add, तो ये खत्म हो जाएगा. So 3x1 is equal to 24. So x1 is 8. So x1 comes out to be 8. And for x2, just put this 8 in either of these constraints. So x1 comes out to be, sorry, x2 comes out to be 7 by 3. So this is 7 by 3. Now evaluate your objective. The objective is to minimize twice x1 plus 3x2. इसका min करना है. So put the value for x1 as 6. 12 plus 9 is 21. 0, 9 is 27. 0, m is 3m. Put this, so you get twice into 9 plus 3m. So 2 से 2 cancel हो जाएगा. So you would end up with 9 plus 3m plus 3m. So 9 plus 6m. So 9 plus 6m. For this you'll get 16 plus 7 is 23. So 16 plus 27 is 23. Now you have to choose the minimum. So this, out of these values, 21, 27, 3 into m, 9 plus 6m, 23, what is the minimum? The minimum value is in fact 21. Occurring at what point? 6, 3. So what is the optima? This corner A is the point of optima. So x1 is equals to 6, x2 is equals to 3, z is equals to 21. Okay. One more thing. Why can't this be chosen? Because m is tending towards what? M is tending towards infinity. So 3m is also tending towards infinity. So roughly, you can treat this value as infinity. And whereas this value is also tending towards infinity. So these two are as it is very large. So the minimum amongst this, and this is 21. Let's say ये तो आंसर आ गया, ये आंसर इस क्वेश्चन का है। लेट्स से द ऑब्जेक्टिव वाज चेंज्ड। इस min की जगह यू हैड, let's say this was not min and this was in fact max. This was maximize. तो रीजन तो सेम बनता। ग्राफिकल मेथड में रीजन का ऑब्जेक्टिव से कोई मतलब नहीं होता, रीजन वही बनेगा जो कंस्ट्रेंट्स होंगी। सी द रीजन इज डिक्टेटेड बाय द कंस्ट्रेंट, उसका ऑब्जेक्टिव से कोई मतलब नहीं होता। वंस यू गेट द कॉर्नर्स यू इवेलुएट द ऑब्जेक्टिव। तो यही सारे आंसर्स आते आपके, यही आंसर्स आते आपके, कॉर्नर्स यही रहते। और आपका ये इवेलुएट होता और ये आपका। अब अगर आपको आंसर चाहिए, नाउ what you want is the maxima. So can 21 be a maxima now? 21 cannot be a point of maxima. This cannot be the objective value. So that means 6,3 a point of optima नहीं रहेगा। So इस वैल्यू में से, इसमें से, इसमें से, इसमें से और इसमें से कौन सी वैल्यू मैक्सिमा है? 21 can't be the answer, 27 can't be the answer, 23 can't be the answer, because you have values that are tending towards infinity. This value and this value both. Okay. So this means for a maximization problem, the answer is that we have the LPP's objective as unbounded objective. So how to decide when you are getting an unbounded objective? The first condition to get the unbounded objective is, first, the region should be unbounded. So the first condition is the region should be unbounded or open-ended. The second is the objective value at the optima should depend on m, that m you have chosen. Okay. जैसे इस केस में ये हो सकता था ऑप्टिमा 3m, क्योंकि बहुत बड़ा नंबर इन्फिनिटी है, बट द वैल्यू एट द ऑप्टिमा इज डिपेंडिंग ऑन m. So this cannot be the optima and this problem is the problem of the unbounded objective. तो रीजन पहला वाला केस सेटिस्फाई क्यों हो रहा है? क्योंकि हमारा रीजन अनबाउंडेड था, हमने उसे बनाया अबाउंडेड एक हाइपोथेटिकल कंस्ट्रेंट डाल के, और वो हाइपोथेटिकल कंस्ट्रेंट क्या थी? x2 being less than m. तो ये जो m आपने लिया ये आपके हाथ में था। So if the objective value at the optima is depending upon m, that means the objective is unbounded. तो सवाल एक ही था, but what we changed was the objective. पहले वाले में ऑब्जेक्टिव min का था, इसमें min का था, तो आंसर आ गया फाइनाइट 21 का। लेकिन जैसे ही ऑब्जेक्टिव बदल दिया, मैक्स का कर दिया, there is no objective value that is finite, and hence we say that the objective is unbounded in this maximization case. So whenever you have regions that are unbounded, open-ended, आपको एक हाइपोथेटिकल कंस्ट्रेंट लगानी होती है जो लगाने से आपका रीजन बंद हो जाए। So I'll just write this. So I'll just write this. So if the region of the LPP is unbounded, the steps that are to be followed is introduce a hypothetical constraint in the problem usually of the type x less than equal to m, y less than equal to k. Okay. Next, find additional corners. Third is evaluate the objective at the new corners also. जो पहले corners निकाले उस पे तो पहले ही कर चुके evaluate. Now evaluate the objective at the new corners also. Next, if the optima value that is the z value depends upon m or k, this implies unbounded objective, or people also say unbounded LPP. See, why is this important is because, see, in this problem we had unboundedness in the region, and since our problem was for a minimization case, see, problem minimization का ही था, region was unbounded but the LPP was bounded. LPP means the objective becomes finite. So LPP का तो आंसर आया है 21, that is finite. So unboundedness can be of two types. First is the unboundedness of the region, जो यहाँ पर है. जो यहाँ पर नहीं है वो क्या है कि यहाँ पर हमारा LPP जो कि मिनिमाइजेशन का था, वो LPP पूरा अनबाउंडेड नहीं था, सिर्फ रीजन अनबाउंडेड था. इस मैक्स वाले केस में क्या हुआ, रीजन भी अनबाउंडेड था और LPP भी अनबाउंडेड हो गई. तो अनबाउंडेड ऑब्जेक्टिव यानी कि अनबाउंडेड LPP के लिए ये दोनों कंडीशंस का होल्ड होना मस्ट है, ये दोनों का होल्ड होना जरूरी है. रीजन अनबाउंडेड हो जाए उससे मतलब नहीं है, उसके बाद अगर LPP का ऑब्जेक्टिव भी अनबाउंडेड आ रहा है तब हम बोलते हैं LPP इज अनबाउंडेड. लेट्स से रीजन होता, कंस्ट्रेंट होती बस एक ये, लेट्स से दिस इज द कंस्ट्रेंट एंड इट सेज टू मूव दिस साइड, मतलब कि अवे फ्रॉम द ओरिजिन है. तो कितने कॉर्नर्स हैं इसके, एक तो ये कॉर्नर है और एक कॉर्नर ये है. सो हाउ टू बाउंड, द सिंपलेस्ट इज एक कंस्ट्रेंट ऊपर से जो ऊपर से बंद कर देगा आप, और एक कंस्ट्रेंट ये राइट में. सो नाउ द रीजन इज क्लोज्ड एंड देयर आर एडिशनल कॉर्नर्स आल्सो. और कौन से कॉर्नर्स हैं वो, एक तो ये एक्स्ट्रा कॉर्नर है, एक ये है और एक ये है. इस ब्लू वाली कंस्ट्रेंट को क्या बोल सकते हो आप, इस ब्लू वाली को कह सकते हो इफ दिस इज से x1 and this is x2, so this can be x2 less than equal to m where is very large, और इसको बोल सकते हो आप x1 less than equal to k where k is very large. Okay, so this is the simplest way to bound your region. There can be other ways also. Let's say एक और एग्जांपल ले लेते हैं सेम बट बाउंड अलग तरीके से करेंगे. लेट्स से यही कंस्ट्रेंट था, यही अनबाउंडेड रीजन है दैट सेज टू गो अवे. सो देयर इज वन मोर वे टू बाउंड. लेट्स से मैंने एक सिंपल स्ट्रेट लाइन खींच दी, लेट्स से ये, तो ही बाउंड हो गया ना. बट प्रॉब्लम क्या है कि इस इक्वेशन को निकालने के लिए इट इज नॉट इतना सिंपल नहीं है. ये तो सिंपल है, हॉरिजॉन्टल लाइन और एक वर्टिकल लाइन. बट इस केस में क्या होगा, एक लाइन ऐसी आएगी आपके पास, द लाइन शुड बी ऑफ दिस सॉर्ट, ax plus by is less than equal to some c. So why get into ax and y both? So the simplest is to make two constraints, एक x के लिए और एक y के लिए, और बाउंड कर दो by vertical and horizontal lines. This can also be done. और आप बोलो कि ये ऐसी है लाइन to state this, but this is usually in this type एक slanted line oblique line बनती है. So that is why people opt for this horizontal and this vertical का combination. Okay, so this is the discussion on the unboundedness of the LPP and the unboundedness of the region also. तो रीजन के अनबाउंडेडनेस होने से ये नहीं कह सकते आप कि पूरी LPP अनबाउंडेड हो गई है. ओके, सो आई राइट दिस आल्सो. सो अनबाउंडेड region does not imply unbounded objective or LPP. But what is definitely implied is if you have an unbounded objective, then this definitely implies unbounded region.